So let's dig in with an example of how we can add address information to our customers by mapping it using owned entity types. So we're now back inside Visual Studio, and we're looking at a new entity class called address. The first thing that we notice is that it has no key property defined. That is because we'll be using this entity as an owned entity type, and as such it will just be a complex type which is responsible for maintaining a subset of information about our customers, in this case address information, and it will have no use for a key property. It consists of 3 properties that can be used to define an address: the street name, the city, and the country. And if we head over to the customer class, we can see that it has 2 new navigation properties that are of the address type. Here we can see the ship to address and the bill to address. So far what we have seen is how we would normally define a one-to-many relationship between addresses and customers. And if we didn't do anything else and created a new migration based on this, that is what EFCore would attempt to infer for us. Except it would fail, since as we may remember from the address class, it has no ID property defined, so EFCore would complain about that. But if we had created an ID property on the address class, we could have used this setup to create such a many-to-many relationship. Doing so would also have meant that EFCore would create an addresses table on the database for us. But since we do not intend to use this entity in any key-based relationships, but rather as an owned entity type, we need to tell this to EFCore. As you can see, there's 1 bit of code for each of the address properties that we defined on the customer class. 1 to configure the ship to address and 1 for the bill to address. As we can see, the customer entity is configured so that it owns both the ship to and the bill to addresses. What this translates to is that the address entity becomes an owned entity of the customer entity, and it is used for both of the relevant properties. It is not enough just to set up the ownership for one of these properties, since that would lead to EFCore complaining that it was unable to determine the relationship represented by that navigation property. Also notice that we called the isRequired method on the street property of both these navigation properties. We don't have to do this, but if we don't, EFCore will give us a warning when we try to create a migration based on this. By making the street property mandatory, we provide EFCore with a property that it can use to determine whether or not to instantiate the address properties on our entity. For example, if the street column is set for the ship to address in one of the entries in the database, EFCore will create an address instance for the ship to property on the entity that we create when we fetch the customer from the database. With this setup done, let's create a new migration for these changes in the Package Manager console. And let's take a look at the migration file this creates. As we can see, what happens in this migration is simply that it adds a number of columns to the customers table in the database. This is the consequence of the owned type being an integral part of its owner, and means that all these navigation properties containing owned entity types will in fact be defined on the table that is mapped to the owner entity. As we can see here, all the new columns have names that are prefixed with the name of their corresponding navigation property, so that the name of the city column of the bill to address becomes bill to address _ city, and so on for country and street. And the same goes for the columns for the ship to address, where the name of the city column becomes ship to address _ city, and so on for country and street. If we now apply this to the database, by running the update database command in the Package Manager console, we can go and take a look at the customers table in the Server Explorer. As we can see here, all the new columns have been added just like we would expect. And if we take a look at the contents of the customers table, we can see the new columns and see that they have all been populated with null values. Let's head over to our program class in the GUI console and add some data to these columns. The first line of code that we see here fetches the first customer in the customers collection, and the next 2 lines that we see here sets up the bill to and ship to addresses respectively. The bill to address is set to be Glendale Boulevard in Los Angeles in the United States, and the ship to address is set to be Hollywood Boulevard in Los Angeles in the United States. And after this, we save the changes to the database. And finally, we fetch the customer once again. Let's try to run this code. If we step past the first line of code, we can see here in the watch view that we've fetched John Doe and that his bill to and ship to addresses are both null. If we now advance the debugger past the next lines of code, we can see that the 2 addresses are populated, and if we expand the bill to address, we can see that it contains the values that we just set. If we take 1 step further with the debugger and save the changes to the database, we can head over to the Server Explorer and take a look at the contents of the customers table once again. As we can see here, John Doe now has the data that we set for the bill to and ship to addresses in the corresponding columns. We can try to fetch the customer once again. But before we do so, we need to clear EFCore's change tracker. We'll do so here in the immediate window by calling the clear method on the change tracker instance of our database context. If we had not done this, we would actually have been fetching the customer from the database context and not as a fresh entity from the database. This is not something we do in production. We only do it here for the sake of the demo. And now let's take one more step with the debugger and fetch the customer once again. And if we take a look here in the watch view, we can see that the two address properties are still populated. And if we once again expand the bill to address, we once again see that it is set to Glendale Boulevard, Los Angeles in the United States. Before we wrap up the demo, let's just quickly look at two features that we can use to alter EFCOR's default behavior when we map owned entity types. Let's head over to the CarvedRock database context and have a look. Remember those long column names that were generated for our owned entity types properties? While these names convey a lot of information, they're not very elegant to look at or work with if we're doing SQL queries directly on the database. So depending on what we prefer, we can actually change this. If we look here where the ship to address is being configured, a new line has been added where we call the hash column name method on the street property, passing in the somewhat shorter name ship to street. If we create a migration based on this, it will change the name of the column from ship to address _ street to ship to address. And if we look here, another change has been added, which is to call the toTable method on the bill to address property on the customer entity. If we create a migration based on this, it will create a separate table to contain the bill to addresses of all our customers. And if we now try to create such a migration, we can see how it implements these changes. The first thing that we see here is that it drops all the columns related to the bill to address. And secondly, that it renames the ship to address _ street column to ship to street. And then if we scroll down here, we can see that it creates a new table for us to contain the bill to addresses, which has all the columns that we recognize from the customers table, plus one more, which is a foreign key that creates a relationship to the customers table. Now let's try to apply this migration and take a look here in the Server Explorer. If we start by looking at the customers table, we can see that it no longer contains the columns for the bill to addresses, and here we can see the new name for the ship to street column. And just above here, we see the new bill to addresses table, which will now contain all the bill to addresses of all our customers. So this was a quick look at owned entity types, where we added the ship to and bill to address properties to our customer entity. So as we discussed, owned entities can be helpful in keeping our entity classes clean, but using them comes at the cost of making our database tables less tidy, as we clearly saw in the demo. As there is with so many things, there is a trade-off here that we need to consider, because we need to weigh the pros and the cons of using owned entity types. And ultimately, whether or not owned entity types should have a place in our data model also depends on how we interact with the database. If we are primarily accessing the database using EFCOR, they may be very useful in the right scenarios. But if that's not the case, the long column names and lack of key-based relationships for the entities might be more of a disadvantage. And now lastly, let's talk a bit about value conversions. EFCOR allows us to define conversions for the properties on our entity types, which basically means that we're able to convert the values that we read and write on the database for those properties from one type to another. A very typical example of this, and also the one that we'll be exploring in the upcoming demo, would be to convert an nvarchar value on the database to an enum type in our entity class. But this description is actually a bit misleading. In fact, such a conversion does not involve the database, but is rather a conversion between a model type and a provider type, which is entirely handled in our .NET code utilizing EFCOR's value conversions. The model type is the type that was specified for the property in our entity class. This could, for example, be an enum type. And the provider type is the type understood by the database provider. The database provider serves as a layer of abstraction between our code and the database, and it takes care of, among many other things, to translate the provider types to something that the underlying database understands. So in our case, where we want to convert to and from an nvarchar type on the database, our provider type would most probably be a .NET string. It's worth noting that the conversion can also be from one value to another of the same type. This could be relevant, for example, in the case of a string property that must be transformed somehow between the database and the .NET implementation. An example of this could be a password that needs to be saved as an encrypted string on the database, but treated as a clear text value in the .NET code. The actual conversion is implemented in the onModel creating method on the database context, as we shall see in the upcoming demo. And there are several options for how we implement it. We'll explore some of these in the demo. So let's take a look at mapping an enum value in our entity class to an nvarchar field on the database. As mentioned, there are a few ways of doing this, and in the demo we'll look at doing so by configuring a value converter, and we'll also do so using one of EFCOR's many built-in conversions. And we should also take a look at how we can use something called pre-convention model configuration to create a conversion that is used on all properties that have a specific type. To implement this, we'll once again consider the configuration that we did in the previous module, where we set up a maximum length on some of the string properties using data annotations. Rather than configuring such a restriction using annotations, we shall instead bulk configure it for all string properties on our entity classes. We're now back in Visual Studio, and we're looking at the customer entity. As we can see here, a new property called customer status has been added, which has the status type. If we take a look at the status type, we can see that it is implemented as an enum with 4 different values: pending, inactive, active, and suspended. This information is used by CarvedRock to decide the current status of an individual customer. If we did nothing further about this new status property and created a new migration, IFCore would infer this to be mapped to an integer column on the database, since the underlying type of the enum that we've created is in fact an integer. But if an integer is not what we need, we can use value conversions to change that. Let's head over to the CarvedRock database context and see how we can do this. The code that we see here sets up a conversion from an enum in our C# entity to a string type on the database. In our case, since we are using SQL Server as our database, it will be mapped to an nvarchar type. We achieve this by calling the hasConversion method on the customer status property of the customer entity. This method configures a conversion on the property, and it does so by taking 2 expressions as input parameters. The first one is an expression that converts the data from the property on our entity before writing it to the database. And as we can see here, what we do is to call the toString method on the enum value. This will return to us the string value, for example pending, of the enum rather than the underlying integer value. The second expression is used to convert the value read from the database to our status enum using the enum.parse method and casting the result to the status enum type. This bit of code creates a value converter that makes sure that the values are converted correctly between the entity type and the database type. Notice that because we haven't specified a default value for the customer status, we might run into scenarios where it hasn't been set. We handle this by checking that the string value read from the database is not null or whitespace, and if it is, we default to returning the pending status. Before we make a migration to see how this will look on the database, we could slightly simplify this statement by using one of IFCore's predefined value converters. IFCore ships with a set of built-in conversions that are usable for a lot of the more common conversion scenarios that we might run into. Converting between an enum and a string is one of those very common scenarios, and we could have done so by instead using this bit of code. What this code does is simply to call the conversion method on the customer status property and simply specifying string as the generic parameter and passing in no arguments to the method. This will do exactly the same thing as the custom value converter that we just created, except for one slight difference. If we create a migration based on this bit of code, it will not handle the case of an empty string just like we did above. So if we use this approach, it might make sense to define a default value for the customer status column. But for now, we'll simply keep the value converter that we implemented above. If we now create a migration based on this, we get a new migration file which we can take a look at. As we can see, what this migration does is simply to add a new nvarchar column to the customers table. Since we haven't specified any max length for the customer status property, it is mapped to an nvarchar of size max. And if we now apply this migration to the database and head over to the Server Explorer, we can see that the customers table now has a new column called customer status. And if we look at its properties, we can see that it's an nvarchar column. Before we try to test this, let's just take a look at another approach we could have used to achieve the same result. First, let's roll back the migration on the database by updating it to the previous migration and removing the migration file that we just created by using the remove migration command.